morning, everybody. Welcome to Wednesday. Hopefully Wednesday is treating you a little bit better than Monday. It's treating me a little bit better. That's for sure. Good morning, Joey and Joey. This is our last set of new material for this semester. Good morning, brain fog. How are you guys surviving? Is it better knowing that there's only like a week left of classes before finals week? Or is it like finals just is this overwhelming loom over you guys? Good morning, JR. A denial situation. That's okay. That's good. That's good. Kind of like, well, that's tomorrow's problem. Joey kind of took the project. Yep, a little behind in some classes. Yeah, and that's the hard thing in anything in life. I'm the type of person that I like things to be done and complete. So it's really hard for me personally to jump around between things. So I completely understand, you're focused on the project, you're I just want to get it done, and then you're oh shoot, I need to get all of these other things done too. Trying not to think about finals week, take care of this week's work. Do you guys, I had a question, I completely lost it. Do you guys have a lot of new material to go over next week, or is it typically review your last week of classes? Matt, you said learning about eigenvectors just in time to apply it in diffie-q. Does that mean you're just doing eigenvectors in diffie-q as well? Which, that's pretty impressive. Although I don't think many students are in diffie-q right now, beyond you. I think you're maybe one of a couple. Oh, interesting. Very interesting. We are going to, eigenvectors can be really useful. They show up a lot. Linear algebra, to be honest, shows up a lot in a lot of material. It's just hiding behind the scenes. We're not really gonna go into much beyond how to calculate things. Oh, I thought they said he's an EEL. I thought he said he's an L, and I was like, eel. Ugh. I thought you said he's an eel, and I was very confused until I realized that's an exclamation point. He's an EE. EEs are pretty cool. I maintain that if I went back and did engineering again, I would do EE or computer engineering, probably. Something along those lines. Maybe computer science. But yeah, we're gonna just calculate eigenvectors today. Which, that's it. Talk about eigenvectors, calculate them, talk about diagonalization, and then we'll be done. And then we will be done. And next week will be all review. There's no set of videos to watch for Friday. Which is great, for me at least. That means I don't have to make them. It means you don't have to watch them. There's no quiz. Morning, JC. There's plenty of spots open for 240 if you want to learn C and C++. C and C++ is it's a different kind of, it's the same programming concepts. There's a bit more to C and C++. It's very much more tied to the hardware. And so you introduce ideas of data types, which just add another layer, and you have to deal with computer memory. And then there's just more when it comes to C and C++. It's interesting to see It's interesting to see the pace of like 240 versus 230. Like in 240, we do variables, and then branching is like week 2, and loops are like week 3 or week 4. Like it's crazy. It's crazy the different pace that you have in 230 and 240, because MATLAB has this linear algebra layer to it that you need to go over, which slows things down because you need to understand the mathematics of the asterisk versus the dot asterisk operators. So yeah, but I teach 240 in the fall, and it's gonna be great. It's usually a smaller class, which is nice. Pros and cons to small classes versus large classes. Okay, it is 9:10, so let's go ahead and finish up the material for this class. So as you guys saw in the videos, we are talking about eigenvectors today. So matrices are essentially, you can think about them, they're when we multiply a matrix by a vector, essentially we are just moving that vector somewhere else in space. So if I have a vector that looks like this, and I multiply it by a matrix, it might move it here in space, it might move it here in space, it might move it here in space. All of these 3 new vectors, moving this one to all those locations, can be done by multiplying my original vector by matrix. So eigenvectors and eigenvalues are these properties where sometimes when we multiply a vector by a matrix, we're really just scaling our vector along that line. So I might scale it this way, I might scale it this way, but it's really as if we just multiplied by a constant. So that's the whole idea behind eigenvectors. And the eigenvector problem, I should pull up the notes. I should know. I know all the pieces, but I completely forgot the formula. Hold on, give me 2 seconds. Oh, it's on the other side. There we go. The notes are here. This equation here we go. This equation here is known as the eigenvalue problem, where that operation, where when we take the matrix, so when we take a matrix and multiply it by, it appears as if we just scale it. We call that scaling constant lambda. This is our eigenvalue, and x is our eigenvector. So x appears on both sides. Okay, so if I look at this equation, I want to verify that this vector is an eigenvector of A. I just do this multiplication. I set up AX, which is 0 to -2, -1, 3, 1, -3, 3, 1. Multiply it by x. When I do this multiplication, I end up with 0 minus 1 minus 3, -2 plus 3 plus 3, and then 2 plus 1 plus 1, or -4, 4, and 4. Okay, so that's AX. If I look at lambda x, let's say I just had lambda in this instance is 4, so if I took 4 times my vector, I would get -4, 4, and 4. So note, these two are the same. This matrix, essentially, for this vector specifically, is essentially as if I just multiply my vector by 4. That's what we're talking about. And this only occurs with certain vectors. So if I took another vector, so let me copy and paste this beauty. Copy, paste it over here. Let's say I had a different vector. Let's say instead of it was -1, 1, let's say it was 2, 1, and -3. And I did the same thing. I would get 0 minus 1 plus 9, 4 plus 3 minus 9, and then -4 plus 1 minus 3. I would end up with 8, -2, and -6. Notice this is not equal to some constant times my vector. So notice over here, this is as if I just multiplied my vector by the constant of 4 with this vector. So this is a special vector called an eigenvector. This would be my eigenvalue. And it only happens with certain vectors. Because notice over here, when I have a different vector, it does not appear as if I just multiply it by a constant. So graphically, this eigenvector over here would look as if I just multiplied it by 4. Whereas this one over here, it would look as if I literally just moved it to somewhere else in space. Okay, so that's the idea that we're coming after. Mathematically, this is what it looks like. Okay, so let's move on to a problem to actually figure out how we can find these eigenvalues and eigenvectors in the matrix. So let's say I have this matrix, and I am told to find the eigenvalues and eigenvectors of the matrix. So we've got our AX equals lambda x problem. If we rearrange this, we get AX minus lambda x equals 0. I just bring this over to the side. So essentially, I'm solving this problem where I can say x, pull out an x, a minus lambda equals 0. So I can mathematically manipulate this equation. At the end of the day, and there's reasons why we do this. Those reasons include, if we go back to on Monday, nope, that's not the one I wanted. I wanted week E notes. If we go back to our notes from Monday, and we go down to this situation here, AX equals 0. Remember, my eigenvalue problem looks like this. Whoops, wrong one. A minus lambda x equals 0. I can pull an x out. This is a homogeneous system. It has a 0 over here. So really, when we're talking about eigenvalues and eigenvectors, we're really just solving a system of equations. We're solving a system of equations to figure out what lambda is and what x is. So when we have a homogeneous system, it's always consistent, which means we're either going to have a unique solution or an infinite number of solutions. The unique solution occurs when x equals 0. So we all know that if x is 0, I'm going to end up with 0. So I don't really care about this one. I don't care about that one. So what we do is we force this equation to have these properties. So we're going to force our a, in this instance a minus lambda, to have a determinant of 0. Once we do that, then we can solve for our x. So that is what we are doing when we're talking about finding our eigenvalues and eigenvectors. So the first thing we are going to do, nope, wrong one, there we go. The first thing we are going to do is we are going to force a minus lambda I to have a determinant of 0. This is called our characteristic equation. Okay, so here we go. A minus lambda looks like this. A looks like this. This is my new A. Minus lambda. When we talk about lambda, we're talking about lambda I, lambda identity. So it looks like that. So once you do that matrix math, you really just subtract lambda from all your elements along the diagonal. So 1 minus lambda, 3 minus lambda, and then negative 3 minus lambda. And I am going to force this determinant to be equal to 0. There we go. There's my characteristic equation. So then you just literally calculate the determinant. That's the word. The determinant. You can use any method you want to calculate the determinant. For eigenvalues and eigenvectors, you're not going to see a greater than a 3 by 3, so you can use the modified Fish method. I'm going to use cofactor expansion along this column here. So plus minus, those are my signs. So the determinant is equal to 0 plus 3 minus lambda times, if I cross out that row and column, I get 1 minus lambda, negative 3 minus lambda, plus 3. It's my determinant of my 2 by 2 matrix that forms. And then minus 0. So there's my determinant. Set this equal to 0. There's two sides. This is my equation to figure out the determinant. This is my side set equal to 0. And then you just simplify. So this one's pretty simple because it already essentially factors out for you. Notice for a 3 by 3, we're going to get a cubic equation. In order to solve for 0, we need to factor a cubic. We need to factor a cubic polynomial, which you probably don't remember fully how to do that. Maybe you do. I don't know. There are more examples on UB Learns. Go look at those if you want more exposure to that. But essentially, it requires long division. But this one's already factored. I encourage, if you're doing these problems, do not multiply out. Do not expand unless you absolutely have to. Okay, so I'm going to simplify this inside. I'm going to keep this the way it is. I need to factor through and expand this. I can't move any farther, so I need to factor through and expand this, which I'm going to end up with negative 3 plus 3 lambda minus lambda plus lambda squared plus 3. And then you can simplify. So here I end up with lambda squared plus 2 lambda plus 0. Factor out a lambda, left with a lambda plus 2. And now I can find my lambdas. So if you have a 3 by 3, you're going to end up with 3 lambdas. Cubic equation, 3 lambdas. Lambda equals 3, 0, and negative 2. There we go. Those are my eigenvalues. This is how you find your eigenvalues. You use the characteristic equation. You do a minus lambda I, which just gives you this matrix. Let's clean it up a little bit. Where you just subtract lambda from all the elements along the diagonal. You force the determinant to be equal to 0. So you are finding your lambda values where your determinant is equal to 0. And the reason why we do this is because of the things we mentioned on Monday, where we have a homogeneous system right here. And if we want to find non-zero solutions, the determinant has to be equal to 0. So these are my eigenvalues. Sometimes you might have eigenvalues repeating. You might have 3, 3, negative 2. It really depends on what your matrix looks like. But you should have 3 of them if you have a 3 by 3. If you had a 4 by 4, you would have 4 of them, etc. Sometimes they repeat, sometimes they don't. And we'll see why we care about that in a little bit. Once you have your eigenvalues, then you want to find your eigenvectors. Like I said, we are just solving systems of equations. So what we're going to do is we're going to take all of our eigenvectors or eigenvalues, plug them into our equation here, and solve. JC, if they repeat, then sure, write it more than once. Yep, just write it more than once. Just to show. So they would repeat if you had something that looks like this: 3 minus lambda, 3 minus lambda, lambda. That would be 3, 3, 0. So just pay attention to what your cubic equation looks like. Okay, once you know your eigenvalues, like I said, we're going to plug it into this equation and solve for x. So you'll have to do it 3 times. If you have 3 eigenvalues, I'll write them back over here. Lambda 1 equals 3, lambda 2 equals 0, lambda 3 equals negative 2. It doesn't matter which ones you choose for which, but they're all going to be labeled 1, 2, 3. So if you have 3 of them, that means you need to find 3 eigenvectors. So you literally just plug each one into that equation and you solve the system. It is tedious. You will not have to do this from scratch for your exam, but you should know what you're doing. So for the first one, we plug it in. A minus 3. When we talk about 3, we're talking about 3 times identity, just like we did with lambda here. x equals 0. Typically, we just jump into writing it in augmented form right away. So for my first eigenvalue, which is 3, I get 1 minus 3, 0, 3, negative 5, 3 minus 3, negative 2, negative 1, 0, negative 3 minus 3. And then my augmented matrix. My B vector is just zeros. In order to solve these, we typically use Gauss-Jordan elimination. And the reason why we do that is because, if you remember, we set it up hold on. We set it up so that we're ending up with this situation where we're going to have an infinite number of solutions. So we're always going to have an infinite number of solutions. If you don't, you did it wrong. And I'll show you how we know whether or not we did it right. So we always use Gauss-Jordan elimination. Okay, so if I simplify this, I end up with negative 2, negative 5, okay, so you have that column of zeros. Don't worry about it. Ignore it. Do it like solve it like normal. Okay, so my row operations, I'm going to say that row, so I make this a 0 and this a 0. So row 2 is going to be 5 times row 1 minus 2 times row 2. And then the row 3 is going to be row 2 times row 3 minus row 1. So 5 times row 1 is negative 10, 0, and 15. Negative 2 times row 2 is 10, 0, and 4. So row 1 doesn't change. Row 2 now becomes 0, 0, 19. And then row 3, 2 times row 3 is negative 2, 0, and 12. And then minus row 1, 2, 0, negative 3. So I get 0, 0, negative 15. And then if I just divide this one by 19, divide this one by negative 15, this becomes a 1, this becomes a 1. So then I'm going to take row 1 equals row 1 minus 3 times row 2, and then row 3 equals row 3 minus row 2. Sometimes our matrices, when we are finding our eigenvectors, appear weird. Like, they just don't fit our standard form, and that's because we're going to get an infinite number of solutions. So the goal is get as many zeros as you can. I can divide this one by negative 2. That'll be a 1. So the goal is to get as many zeros as I can. Notice this final matrix looks like this. It doesn't look like our standard form. Typically, we would have it looking something like this. And sometimes you might see that as well. But however it ends up, that's fine. Don't worry about it. Still write your system of equations. This one tells you that x1 equals 0. This one tells you x3 equals 0. You have no information about x2. That means x2 is going to be your free parameter. That means you can choose x2 to be any single number you want. Remember, we're ending up with an infinite number of solutions. So my vector, my x, really looks like this, where t is any number. And when we're talking about eigenvectors, it's really a whole set of eigenvectors, where it's any combination, any scalar multiple of this vector here. Typically, we just choose one, and we choose one with the smallest whole numbers. Typically, you don't have to. So typically, I would say x equals 0, 1, 0. This would be my eigenvector, when in reality, it's any scalar multiple of this. Okay, so let's write it down over here so it's nicely combined. x1 equals 3. My corresponding eigenvector is going to be 0, 1, 0. So if I multiply this vector by my A, it's appearing as if I just multiplied it by the number 3. Okay, I need lots more space than I anticipated for. Okay, so that's my first one. Notice I ended up with this row of zeros. If you do not end up with a row of zeros, you did it wrong. We want an infinite number of solutions, so therefore we need that row of zeros. So let's do another one. Okay, x2, lambda 2 equals 0. So I'm going to plug it into the equation, a minus 0I, x equals 0. Which gives me 1 minus 0, 3 minus 0, negative 3 minus 0. And then this side is all zeros. When I do that math, I end up with A. Okay, there's my system. Now we do Gauss-Jordan elimination. Start by making these zeros. So I'm going to say row 2 equals row 2 minus 5 row 1, or plus 5 row 1, and then the row 3 equals row 3 plus row 1. So 5 times row 1 is 5, 0, 15, 0, negative 5, 3, negative 2, 0. So row 1 doesn't change. Row 2 becomes 0, 3, 13, and 0. And then row 1 plus row 2 becomes 0, 0, 0, 0. There's my row of zeros. Woohoo! I did it! Note, this one's almost done. Depending on what A looks like, these problems are actually pretty simple. Like, there's not many row operations to have to do. It's nice that these zeros are already here. So if those weren't there, you'd probably have to do a couple more row operations. But regardless, you should end up with your row of zeros because we want an infinite number of solutions, because we are forcing it to be that way, because we force the determinant to be equal to 0. So the last thing I need to do is divide this one by 3, technically. So my final RREF looks like this. So technically, I need my 1s in my pivot locations. Once you have that, write your system of equations. x1 plus 3x3 equals 0. x2 plus 13 thirds x3 equals 0. x3, you don't have any information about it. That means it's a free parameter. Simplify this. x1 equals negative 3x3. x2 equals negative 13 thirds x3 equals free parameter. Like I said, this is a whole system of vectors. Technically, negative 3t, negative 13 thirds t, and t. We typically choose the one that gives us the smallest whole numbers. So I'm going to choose t to be 3, or x3 to be 3. So I get negative 9, negative 13, and 3. So here's x2. If I multiplied this vector by a, it would appear as if I multiplied it by 0. It's really weird. Like, you're like, oh, there's no way that ends up as 0. But it does, because lambda 2 equals 0. So x2 looks like this. And you can choose x3 to be any constant you want. You can choose x3 to be 1. But then x2 would be negative 13 thirds, and x1 would be negative 3. You could choose x3 to be negative 3. Typically, though, we choose the one that ends up with whole numbers, but really you can choose whatever you want. Just know your eigenvector is one of them, and any scalar multiple of that vector will also work. So we've done this for 2 eigenvalues. We have 3, so we need to do it one more time. Oh, come on. More space. Maybe I write bigger than I thought. Okay, so lambda 3 equals -2. So I plug it into my equation. A minus -2i, x equals 0. Solve for x. Plug it in. 1 plus 2, positive 3 plus 2. -3 plus 2, 0, 0, 0. -1. Same stuff I've done. Start out by finding my zeros. So R2 is going to be 3 times row 2 plus 5 times row 1. R3 is going to be 3 times row 3 plus row 1. Row 1 doesn't change. I could also start by dividing row 1 by 3. That would actually probably be better. I'm going to do that first. Make it simpler on myself. I'm going to say row 1 divided by 3, so that becomes a 1 and that becomes a 1. There we go. Now I can say row 2 equals row 2 plus 5 times row 1, and row 3 equals row 3 plus row 1. Make it simpler. So we've got 5, 0, 5, -5, -1, -2. On your exam, make sure you are clear about everything that you're writing out. Like, write that as its own, like if you're dividing by 3 for this row operation, write it as its own separate row operation. Shouldn't the 2, 2 value be 5? 2, 2, 2, 2, 2, 2, 2, 2. Yes. Thank you. You know, I did solve this out on paper. You'd think I would check my work. But I like making math mistakes, right? Those are great. I love minor math mistakes. They solve all my problems. Okay, so row 2 becomes, that was sarcastic. 5 plus -5 is 0, 5, 3, 0. And then row 3 becomes 0, 0, 0, 0. There's my row of zeros again. I love it when it shows up. It means I did everything right. Woohoo! And notice I'm already in RREF once I divide this by 5. So I end up with 1, 0, 1, 0, 0, 1, 3/5. There we go. Write my system of equations. x1 equals -x3, or x1 plus x3 equals 0. This one tells me x2 equals -3/5 x3, or x2 plus 3/5 x3 equals 0. And this one tells me that x3 is my free parameter again. Which means my set of eigenvectors looks like this. -t and -3/5 t and t. Once again, choose whatever value you want for x3. I'm going to choose a value of -5, just for kicks and giggles, which means x2 becomes 3 and x1 becomes 5. There we go. So if lambda 3 equals -2, x3, my x3, is -5, -3, and 5. Really, any eigenvector that is a scalar multiple of this will work. There we go. If you ever want to check your work in MATLAB, it's not that hard. Just go to MATLAB. You plug in all your values. So you plug in your A. A looked like this. If you want to confirm your eigenvectors, you can use the Eig function. So EIG, that's not right. Oh, typed an A wrong. Shocking, I know. This is a positive 3. So A looks like that. Then you can type in Eig. Yes, so Joey, you will be working with at most 3x3s. We won't ask you to do this for a 4x4. So there we go. So you type in A. If you want to check your eigenvector or eigenvalues, just type in Eig. You can't check for your eigenvalues. You can do the RREF. So you could say RREF, and I like to do this. RREF function, A minus, well, here times I 3 next to 0 is 3 comma 1. So like if you actually plug in your equation, so A minus lambda I x equals 0, and solve for it using RREF, you can do this to check to see if your Gauss-Jordan elimination was correct, but it will not interpret it for you. It will just give you your system of equations. You still need to figure out how to find your eigenvector. However, if you have your eigenvector, you can check to make sure that it works. So our x1 was equal to 0, 1, 0. So you could say A times x1. And see, oh yeah, that is multiplied by 3. That is like I just multiplied it by my corresponding eigenvalue. That's great. That's amazing. And you can check for your next one, which is my favorite because our eigenvalue is 0, and it's like mind-blowing. Like I did the math on paper and I was like, what? It actually makes sense. Then the second one was negative 9, negative 13, 3. So here it is. If I say A times x2, I get zeros. Like it's weird. Like you're not like that matrix times that vector gives you zeros? Really weird. So yeah, so there you can check for your second x value, your second eigenvector, and then same thing for your third one. Third one, we chose negative 5, negative 3, and 5. If you do A times x3, you can confirm, yeah, that's multiplied by negative 2. So you can confirm that your eigenvectors match what you should expect if you multiply them by your A matrix. Okay. I don't know why I found it amazing, but like, I multiplied A times x2 completely forgetting that my eigenvalue was 0, and I multiplied and I was like, I get 0? And I was like, oh my goodness, it works. Like, that's crazy. Just because like all of them end up being 0 is kind of special. And I mean, that's true for any eigenvalue. Like, it's pretty special that this ends up being 2 times each one, but 0 is just a more magic of a number. Okay, so that's that problem. You can confirm in MATLAB your answers, which is great. Back to notes. There we go. That's what I'm looking for. And my header was not correct again. I really should take that off. On the last day of classes. Okay, so the last one is this concept of diagonalization. So diagonalization is the idea where we are, it's called decoupling a system of equations, or decoupling a matrix, not a system, decoupling a matrix. It's, once again, the same way why we do LU factorization. There are some nice properties we can get out of the diagonalization of a matrix, which is great. We are not going to go into those. I'm just going to show you how to write the diagonalization, and once again that it works and how awesome it is that it works. But if it says find the diagonalization of A, here I'm given A, and thankfully I'm given my eigenvectors. I'm not given my eigenvalues, but I can easily find my eigenvalues given my eigenvectors. All I need to do is I know that AX equals lambda x. So I'm going to take each A, multiply it by each x. So if I do this, I should figure out what my eigenvalue is going to be. So here's x1. So if I multiply A times x1, I get negative 1 plus 0 plus 0. Then I get 0 plus 0 plus 0, 0 plus 0 plus 0. So I end up with negative 1, 0, 0. There's lots of zeros in there, makes it kind of nice. Which means that this vector and this vector are the same, except multiplied by negative 1, which means lambda 1 equals negative 1. So I found my first eigenvalue. Woohoo! So there's lambda 1, x1 was 1, 0, 0. I can do the same thing with x2. Handy dandy copy paste. X2 looked like this. 5, 0, 4. If I do this multiplication, I end up with negative 5 plus 0 minus 20. 0 plus 0 plus 0. 0 plus 0 minus 20. Or negative 25, 0, negative 20. So this vector and this vector are just the same, but I multiplied it by what appears as negative 5. So lambda 2 ends up being negative 5. X2 was 5, 0, 4. So I've got 2 of my eigenvalues. My third one. Paste. X3 is 1, 1, 1. If I do that multiplication, I get negative 1 plus 4 minus 5, 0 minus 2 plus 0, 0 plus 3 minus 5, or negative 2, negative 2, negative 2. So here, this vector and this vector are essentially the same, but it's like I multiplied it by negative 2. So lambda 3 is negative 2, x3 was 1, 1, 1. Okay, so if you're ever asked to find the diagonalization of a matrix, you need to first identify what your eigenvalues are, and then your corresponding eigenvectors. One key thing to note is that in order for a matrix to be diagonalizable, nice job, subtitles, you need to have 3 distinct eigenvalues. So in order for a matrix to be diagonalizable, you need to have 3 different eigenvalues. If you had repeating ones, you could not do the diagonalization. And we will see why in a minute. So this matrix up here, this last example, we found 3 different eigenvalues, which means this matrix would be diagonalizable. This matrix down here has 3 different eigenvalues, so it is also diagonalizable. Okay, once you find your eigenvalues, they're distinct, you're good, you can move forward. Once you find your eigenvectors, your diagonalization is almost done. The diagonalization of a matrix can be written like this: x inverse ax equals capital lambda. This is a capital lambda. It looks like that. Greek letter. Typically we see lowercase lambda, but that's uppercase lambda. And each of these matrices is pretty easy to find once you have your eigenvalues and eigenvectors. A is A. A just looks like A. A was this. So here's A. It's your original matrix. X is going to be all of your eigenvectors placed in a matrix. So you literally just place them as columns in a matrix. So if x1 was 1, 0, 0, make that your first column. If x2 was 5, 0, 4, make that your second column. If x3 was 1, 1, 1, make that your third column. You literally just put in your eigenvectors as columns. You may have guessed x inverse is the inverse of x, which we know how to find the inverse of a matrix. We've done that. You can use Gauss-Jordan elimination the long way. You can use your cofactors the short way. You can use MATLAB if you're told. You can use MATLAB. I'm going to use MATLAB, so I'm going to gonna plug in x equals 1, 5, 1, 0, 0, 1, 0, 4, 1. Inverse of that. There we go. X inverse looks like this. 1, 1/4, -5 fourths, 0, -1/4, 1/4, 0, 1, 0. Woohoo! So nice. So there's x inverse. Lambda, so if we do this multiplication, let's do it. Let's do it in MATLAB. So I have A, nope, that's not my A anymore. A looks like that, -1, 4, -5, 0, -2, 0. I can do split. There we go. -2, 0, 3, -5. I have my x in there already. X inverse is inverse of x. Okay, I have all my pieces. I should do x inverse times A. Oh, come on. Times x. Notice the order matters. What? We get a nice diagonal matrix of -1, -5, -2. That's what we get. Notice those match our eigenvalues. So this first one is our first eigenvalue. The second one is our second eigenvalue. The third one is our third eigenvalue. That is our diagonalization, where we can break A up into these three pieces so that if we do the multiplication, we end up with a diagonal matrix with the eigenvalues along the diagonal. I do want to point out that the order here matters. The order here matters. If this is x1, it corresponds to lambda 1, the first row. If this is x2, it corresponds to the second one. So this order matters. If I had arranged x so that it looked like this, my lambda would also be rearranged. It would be, so this is x3, this is x1, x2. It would look like this. x3 would be my first one, x1 would be my second one, and x2 would be my last one. So the order matters. So if you do x1, x2, x3, your lambdas also need to correspond. And that's it. That's eigenvalues, diagonalization. We're really just, it's based off of this idea where ax, not an a or an x, ax equals lambda x. Or a minus lambda I, x equals 0. These are your two main pieces. If you're ever given a and you're ever given x, just start here. You can figure out what lambda is. Unfortunately, if you're given a and you're given lambda, you can't find x using this equation. But if you're given your eigenvectors and a, just go here right away. If you're asked to solve for your eigenvalues, you need the characteristic equation where we are forcing the determinant of this matrix to be equal to 0. And then if you're ever given lambda and you're asked to solve for your eigenvectors, solve this system. So this is my augmented matrix. Solve this system using Gauss-Jordan. You're going to get an infinite number of solutions. Pick one. Because really, for our eigenvectors, it's any scalar multiple of whatever value or whatever vector we picked. Okay, that is all I have for today. That is all our material that covers like all the calculations you should have to do for eigenvectors. It can get long if the second problem, notice the second problem for calculating all of our eigenvalues and all of our eigenvectors, it does get long. It does get repeated. Just be aware of everything you're supposed to do. And what pieces you might be given. JR, do you think we'll know our grade on the, yes. So we always want the TAs and graders to finish the grading on the project before the final exam. So in our instructor meeting tomorrow, we'll probably reiterate that to the TAs. I sent them instructions on how to grade it on Monday, so hopefully there is some grading going on. But yes, in theory and in practice, usually, and I always try to make sure this is the case, that you have all of your grades for everything before the final. Keep in mind, and when you're going into the final, I do have that grade calculating spreadsheet on UB Learns. If you want to use that, you can enter in all your grades and you can play around with what grade you might need on the final in order to identify what grade you will get overall. Remember, the grade this class is not curved. We might lower the cutoffs, but usually we don't. It depends on the semester. Also, I just want to brag about you guys. This semester has been phenomenal. Like, you guys as students, you just blown me away with everything you guys have accomplished in this class. I opened up my grade book on Tuesday morning, and this never happens. I opened up my grade book and everybody had a submission for the project. And that has never happened. I was just flabbergasted. Like, I just bragged to my husband. I was just like, this is so awesome. Like, I've never seen this before. This is amazing. So, really, just this semester has been way more than I ever thought it could be. And really, it's all on you guys. I just wanted to brag about that for a minute. But yeah, so for the final, you can use that spreadsheet if you want. Like I said, most semesters, I can't think of a semester where where students haven't had all their grades. But remember that your lowest homework grade will be dropped before your final is calculated, or before your final grade is calculated. So keep that in mind. So the grade you see on UB Learns is really the lowest grade that you can get. Anyway, so that is all I have for today. Are there any final questions? Next week will be all exam review. I will have lots of examples, as many examples that I can go through. If I don't get through very many, I will make more videos, all that fun stuff. The homework solutions, yes. The homework solutions, I haven't posted any for linear algebra. I will have them posted by this weekend. I'll have them all posted before next week. What will the exam be like? The exam will be like solving problems. It will be linear algebra. You'll be writing problems. There will be a practice exam, which should be up before the end of the week. Just like with the midterm, the best thing you can do is do your homework right now. That is the best way to study, the best way to practice, because it's going to be linear algebra problems. They're going to look a little different in the sense that you're not going to have all numbers. You might have to solve for a given number in the matrix, given some constraints. But like I said, we will... JC, you can email me, and I can tell you why you got the point off. Yeah, we'll go over problems next week. Best thing you can do right now is do your homework. Yep. Okay, any final questions? before I head over to office hours. If not, I will see you guys next week.